All right, let's get started. Welcome to another Common Lisp Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. Today we're going to be continuing our ongoing adventure into Forth in the Forth interpreter that's built in Chapter 8 for Let over Lambda. Last time we ended with the definition of unary word definer, which is a way for us to grab from Common Lisp a bunch of predefined Common Lisp words and adding them into our vocabulary, into our Forth vocabulary. So in our Forth interpreter, we could just leverage these functions without having to redefine the actual Common Lisp functions themselves. Today we're going to be continuing in that, guys, adding binary word definer, as well as talking about some additional, going into a little bit of depth into how the threading model works in Forth, and adding a couple of what Forth, the book calls naked primitives, which are Forth primitives that don't actually interact with the program counter of the Forth abstract machine directly. Instead, they do some command line logic to control it and update it themselves. So the abstract program counter, if you recall, in our inner interpreter, it gets updated when an operation gets, or a word gets found. That inner interpreter actually goes and updates the program counter to make sure that it points to the right thread or code block to actually go and execute. These primitives that we're going to be covering today do not do that. They update it directly. They don't let the inner interpreter go and deal with the program counter updates. Hopefully, we will complete all these additional ones, because these are actually all necessary to build up to the final section, which is actually implementing some Lisp on top of our Forth interpreter. So we'll be going pure meta into that pure meta world, and it'll be pretty fun. Things to just be aware of. I went ahead and, for folks following along, I don't know if you had a chance yet from last week, but if you haven't, all the code that I have done up until this stream is available on the Atlanta Functional Programming GitHub repository with comments. Couple things to note on that when you do play around with it. One of the issue with when you're running the library in your Lisp image, where when you're redefining one of the functions and need to define some other dependent macros at the same time, and those are particularly sections that have this eval len in there. Places where we're using the hash backquote, the sharp backquote reader macro that we've written in episodes past, you will get an error if you do not do what I'm displaying here, which is change the read table to being reader macros. The reason is by default, the reader macros that are defined in this project are not part of the standard read table. And when when this library gets loaded up, it changes the read macro only for the lifetime of loading up the file and compiling it. So all those will get compiled ahead of time. But if you're trying to redefine it, you're going to have some issues if you don't change the read table in your Lisp image. When you do that, once you redefine stuff, good practice is to change it back to either named read tables, in read table current, or standard. Usually current and standard are the same thing, but if you have other dependent read tables in your Lisp image, current will probably have more of the amalgamation of all of the currently loaded read tables ahead of time. I'm still trying to figure out a way to register this so when you have the read table in the Lisp image and you loaded up the project, you don't, that read table is part of the current read table with everything else. I haven't found a good way of doing that. Folks who are following along and are aware of how to get that so that redefinition of functions can actually happen in a little bit more consistent manner like we would do any other Lisp redefinition, do let me know and I will update the code as is. But until then, my suggestion to folks is to use this workaround instead of trying to figure out a way of changing the read tables and loading up the file, because that just causes a lot of weird headaches. And this will at least let you go and experiment further through the actual Lisp interpreter. The fourth interpreter itself, and trying things out in there, rather than doing what we did last time in our last episode, where we ended up having to restart the REPL every time we wanted to reload a redefinition of an existing function. So let's talk about binary word definer. Binary word definer is kind of like our fourth unary word definer function, but there is a slight difference. It does the exact same thing in essence, which is it's going to grab a bunch of Lisp functions that are already available for us. 1 second. Lisp functions already available for us into our fourth vocabulary, but the difference is for certain functions, the semantics of that function needs to be accounted for a little bit differently. I'll give an example. Subtraction. Most people know that in Common Lisp, when you do subtraction, usually it is first it's first value minus second value. When you're using fourth, though, if you recall, what ends up happening is we would be adding this in the order in which we're typing it in, thinking like it's 5, 4, minus. But that will give you, obviously, -1 instead of 1. Why? Because of the fact that fourth, since it's is stack-oriented, it's going to take the top of the stack, 4, as its first argument, and not 5. So what ends up happening is the order is reversed, and then you end up getting an incorrect value. So we need to go and fix that. This is not a big deal, but it does change the way the macro has to be created. So let me first check one thing, because I forgot to do this before the stream, but please bear with me. We're going to be using Alexandria's with gensims function, but I need to first verify that Alexandria is part of this project. And then, seriously, it's taking a second. Locked up. Uh-oh. SpaghettiOs. 1 second. There we go. Go up. 2. So much easier just to do this. Okay. And yes, it is. Okay, great. X, B, mean. All right. So we're going to be handling binary word definer. We're going to be defining binary word definer the following way. Now, again, those were reading LOL and trying to do a direct port of some of the code examples there. I'm not doing a direct port. I'm converting it so that we have actually standard common Lisp available for us instead of using the def macro bang that's in Doug Hoyt's examples. So this is one of those where we do need a gensim to actually keep track of some information, and I'll get there when we're defining it first. So our fourth binary word definer is as follows. So we grab all the words, we go ahead and we do a prog n, because this is going to be multiple statements. We're essentially defining, remember, like before, a fourth primitive. Here we're going to go ahead and do a map car of the following. We are going to define fourth primitive, and we use our A1 nil because, again, remember, this is being defined inside our inner interpreter's redefinition function, which is using an anaphoric macro to keep track of the symbol that's being used inside of the definition, and that's captured by the A1 anaphora that's part of our sharp backquote reader macro. Now we need to, again, like I said, we need to preserve the semantics of the binary word, the binary operation that we are actually encountering. Now, some of this, flipping the order of operations is okay. Now, for example, if you think of addition switching the operations is fine because addition is commutative, a plus b equals b plus a. But to preserve minus and some of the other ones, we're going to have to change the ordering. So, to do this, what we'll do is we would use Alexandria with Jensen's top, and we do let top top. They have to become top there. Yeah, I'm pretty sure I have to do that. We'll see if that causes issues when we do macro expansion. We're going to grab the top of the stack, okay, and we're preserving it, and then we're going to push essentially the operation, take the top of the stack, and then provide the bottom of the stack. All right, and then we're going to grab that and put it into P stack here. And oops, I may have missed one more here, and then words. That's our thing, and we're done. All right. So let's go ahead and define this. There is one thing here that I need to make sure. And let's define the pre-strings. It looks right. And let's go and check that. Yeah, that looks correct. Okay, let's go ahead and compile this guy. Undefined variable top. Okay, so this is here. Let's see if, oops. That's what I needed to do. All right, so we didn't have to unquote that. All right, let's go look at how this might be used when we're defining minus. All right, I'm going to go ahead and do this generation here. Pull this up so for folks can actually look at it. Macro expand fourth binary word definer minus. Boom. There is something that I am incorrectly defined. Oh, my apologies. I defined it in the wrong order. This should actually be done before we define. That's the reason why I aired on it. In fact, you know what? I think what I have to do is do this. Okay. Compilation failed. What is that? Right? We may have messed this up. Just give me a second. Oh, it's not liking the fact that I'm trying to do this behind the scenes, isn't it? Got it. Let me do this. Put this here. Yeah, no. This has to actually go into. Pretty sure that this is correct. Hold on. Use root Jensen's elsewhere in here, don't we? This is correct. The only thing is this and this. Let's see if see. The word top is defined but never used. Yeah, so that's right. And this is right. It should avoid that. Words. Oh, that's why. There we go. Because I changed the ordering of the operations. I didn't change the parenthesis order. Rookie mistake. My apologies, folks. Just double checking to make sure now that everything is right. Yeah. Better. Alright, let's do this again. Yeah. So if you look at this expansion, what it does is it's taking our generic primitive. This is what the G exclamation point does, and in combination with the def macro, bang macro that let over lambda defines. We took a generated symbol top, and what we did is we grab the top of the stack, and we temporarily keep track of it because we don't need to operate on it just yet. We're changing the order of operations, recall. And then what we're doing here is we are going to be changing the order in which the functions are going to be applied. Now, we can use this to now define the following very quickly. We could use this same one to define fourth binary word definer the following functions. We could do EQ equal for string equal, equality, EQs for cons equality. We can define plus, minus, divide, our equality operators, our logical operators, both strict logical operators as well as the more lenient ones, as well as max, min, and or. Again, like before, when we define this, just like everything else, we now have these part of our inner vocabulary that if we go in and define, and I'm just doing this as a sanity check, usually you don't need to do this, but just in case, I recompile our fourth interpreter, and then if I just go ahead and, the setf new fourth interpreter, and if we do go forth, new fourth, and we do, let's say, 5 4 minus unknown relief in compilation mode, it will be command step. Let's go in and check now our Pandoric macros with Pandoric p stack on our new fourth p stack, and we'll see that we have -1 there. Actually, that's incorrect. That should be 1. Why is that? Okay. Let's see here. That should be the correct order of operations. 5 4 minus, it's not -1. If that means that this guy for 5 minuses. Yeah, that is wrong. No, that is correct. Because the fact that we're grabbing the top of the stack and then applying that as being no, that is incorrect because that means it's generating the wrong thing. Let's go look at the macro expansion again. Okay, we let the top be the top of the stack. Then we pop the stack. Push minus pop stack. But that's, so this means that this guy is incorrect. Alright, let's do something, folks. Let's do this. When in doubt how this kind of works, let's go back to the original order. Let's do 5, 4, and let's go ahead and run pstack. So the top of the stack is 4. Okay, we can do this another way. I'm going to redefine everything just a sec. So print. I'm going to try printing out our value here. So that way we could see what is actually being popped off when we exercise this. These guys are all redefined. And then we do go forth. Oh, right. My apologies. I have to go and redefine the interpreter. One second. Okay. Keep it here. Split. Split. Go up to in the interpreter. There we go. This guy. Not compiled now. Let's go into this. Weird. Did not generate anything. Okay, I'm gonna come. New print. Let's do format T at top of stack. Do that. One second, I just noticed that we had a question. What's Forth a reference to? Forth is a programming language. Let me just pull this guy up for you. Let's see here. Let's do this. Let's see what happens here. Interesting. Wonder what macro expansion. Where is my macro? My guess is it's not actually grabbing that, but let's see what pstack returns. Pstack still returns -1. Interesting. That means it's still actually doing what I thought. It's not doing that. Instead, it's doing this, essentially, which is odd, given the fact that the macro expansion looks correct. So what else could it be a problem with? Let's think about this for a minute. This is a correct description, but and it's generating the correct definition because it's able to execute it. Then it's not even printing out to console, even though I explicitly said to print it out. So let me see if I can actually look at. Oops. Let me go and look at. That's what I can do. Let's look at the code. It's actually generated. With Dict, you can actually go and look at using fourth word thread, fourth lookup, minus in our dictionary. It's a function. So let's see. Okay, drop. Okay, let's do 6 3 minus. Let's see what happens here with our p stack. It's still 3 minus 6. One second. There's this unknown value that I wrote here. This can be taken out since we don't need this anymore. This is working now. But the way it's compiling the order of this is incorrect. So let me go and take a look at that. Format TA to the top of this part. So it's ignored. And it is a bit odd. This should actually print out something. Generating this. Let's go into defining our port interpreter again. And then let's do this. Still minus 3. What is going on there? let's do this. Got it. Add this, go forth. Creates a new forth, goes and combines it. The word list is uncall that. Uncall. So the problem is, I mean, everything else seemed to be worked, so I doubt it's this, but we could see this. Do that. Let's go to our inner interpreter. There it is. Actually, you know what? Let me take that back. That's going to be in this function. Handle not found. Otherwise, push V onto the parameter stack. And it will try to compile. Oh, sorry. If in compiling mode, it won't compile this because it's not in compiling mode. We'll just put the parameter in. So this should be correct, but okay. So this should be the top of the stack should be where's our parameter stack? Should be 3, right? I'm going to do this here, which is immediately previous word. P stack, we only have pointer in the program content. Okay. Do that. Let's add a plus, which will cancel out those. Then add a 3 back. I want to return the parameter stack back to what it was originally without having to create a new instance of our interpreter. So if you guys see some weird, what arithmetic is this guy doing? Why is he just changing stuff back? It's because I was just putzing around with it a little bit. This is odd, folks, because of the fact that the order of the macro expansion seems to be correct based on my expansion. And not to mention, I verified that it's actually what is the generated code in the book as well. So we just need to figure out why this is particularly causing this weirdness. Let's do a quick handle found. I'm going to go look at what handle found does. If compiling not immediate word, otherwise it sets it to the 4th word, and then calls the inner interpreter. And our inner interpreter, so it's a problem potential in our inner interpreter. fun call. Let's see here. I'm going to change some stuff here just to see what's going on here. So here, let's do this. XSP background. Just adding some interactive debugging, some debugging statements, just to see what's going on with the interaction of this RPC. So this guy here is going to be that. This equals that, so we don't get any weirdness there. I'm good with that. I'm going to go ahead and do this too as well. Into pstack and setting. RPC. Okay, so this should give us enough information on what is going on. Okay, let's go to the new fourth interpreter. And when you're doing macro debugging, this printf, I usually go back to print debugging. In another session at some point, I should try to dig into debugging macros a little bit more more detailed than doing this, but the macro expansion plus the debugging would tell you some of the runtime characteristics of particular macros. Okay, let's do that. Push email. Okay, so this is just getting some of the, ooh, okay, I see what it's doing. And, okay. Now, let's do this. So I just set my fourth interpreter down. Let's go ahead and do go forth. Six, three. Oh, I should have dumped it, but didn't. Oh, that's because it didn't. I didn't call minus. Sorry, let me do this again. Calling closure. Then let's see. And it still ended up going in the wrong direction because it's already like it's too late here at this point. So let's add a little bit more flavor. Go ahead and change these out because this is the wrong location clearly. Okay. It's going to fourth handle found. Let's add one more thing here. Calling with. I wonder if I can actually incorporate p-stack. Let's see if I can do this. Fourth word name word and p-stack. Alright, now just one more. Sorry. Okay. I'm gonna go restart my my Rebel. This is odd. The redefinition doesn't seem to be working. Actually, you know what? No. Go up to inner interpreter. May have done it wrong. Fourth inner interpreter. Nope. This is right. Yes, it did not like that. Let's see. There we go. That's correct. Because I added alright, so now so it is calling minus with the appropriate p-stack. But then why is it doing that oddity? My treating car has the top of the stack or the bottom of the stack. It should be the top of the stack. For some reason, it looks like it's the bottom of the stack. Let me do something here. One easy way to know if my program counter is messed up is to check to make sure in our inner interpreter that we're always pushing the program counter into the parameter stack. This is right. We're pushing it. We're setting the cutter, the rest of the list to the pointer so we can keep moving on. So that's how we set up the lexical scanning. This is going to be then set up correctly so that it's set up for the piece. We have code is set fpc to the clear of the PC. These are all stuff that we defined in previous things, and they worked well. Ah, I bet you that's what's happening. Right here. This is wrong. All right. So we need to go and redefine that. Okay. Go back to our dictionary here. Use fourth interpreter to create our things correctly. And I forgot I defined that earlier. Okay. And where's our p stack say? Let's see here. Oh, those are already added to the standard library. Crap, I think I'm going to have to restart my Lisp. Sorry, folks. The font size, just like I said before, got to do me max deciding that, oh, your previous font that you decided in this buffer is not right, so I'm going to go reset it. Okay. Quick load, or do fourth demo. Package. Okay. Boom. This is looking promising. Yes. All right. That was the problem. Man, that took a. Should have recognized that. So the issue is earlier in our episodes when we were defining the primitive operations, all these primitive operations that I added back from Common Lisp into our fourth interpreter, these aren't actually valid anymore because of the fact that these guys are operations that we're going to be grabbing from our Lisp. So we're going to go ahead and for now we are graduating into actually using Lisp and fourth together. So those are gone. Actually, I'm going to keep these for historical purposes for folks who are watching this, as well as for folks who want to dig into how to do like symbols of different. Is there a way to create like a dictionary of dictionaries? Because fourth does allow you to do that. You can have different dictionaries with different symbols, but I don't know about how it does name conflict resolution, which is essentially what this was. This was the fact that we had two operations with the same symbol, essentially the same word name, and it found the first one and applied it. So let me go back to, let me clean up some of this stuff. Do this. That's fine. Let's go comment this. This guy out. And in fact, what I'm going to do is I'm going to move this to be later on. All right. All right. Okay. Let's move on. So what you've now seen is essentially, a little bit of some debugging on how to create the binary word definers, and we can add certainly more from common lists. I think the majority of the ones that we defined here are the common ones that you would see in fourth anyway. So this for now will be what we'll be defining from common Lisp into for our fourth interpreter in terms of binary word definers. The main thing that you want to make sure of you understand is this particular piece of code here, from line 267 to line 277 inside main.lisp. Again, I'll check this in at the end of this this stream. Again, this is converting the stuff from let over lambda into standard common Lisp, so it's using gensense the way it was intended. We're using a mixture of our anaphora and our reader macros had we defined in previous episodes. Generate some examples, and you could structure. You can certainly get the gist of what this is essentially doing, which is just defining a new fourth primitive for every new dictionary word that we provide here in this list. So it's looping through this list of words, and for each of these, it's treating the name also has the operation that you're trying to execute, which is how you would normally do lookup inside Common Lisp anyway for intern symbols, and will then define the operations the way it was normally intended. So let's now move a little bit forward in talking about what we've been, talking through in terms of fourth code that we've seen so far. The majority of our fourth code that we've seen so far have been, for the most part, have been graphs, directed acyclic graphs specifically. They have no cycles. There is an ending point that guarantees termination of the code. Since we're not leveraging the console structure to create like infinite lists or circular lists, it's not, it's an actual proper tree. It's kind of interesting that we can leverage this with our with Pandoric macros from past, from what we've implemented in the past, to actually go look up one of the how a particular piece of code is actually structured. An example of this is going to be if we defined a a function called Cortec. Now, this was defined earlier in the book for folks following along, and I forgot that I did not define square. Give me a second. Where are you, square? There you are. So let's go ahead and define square, and then define Cortec. And let me just go ahead and do one thing here before we continue. Fourth handle found. Okay. I'm going to do this again. Oh, apologies, I did this again. Named read tables in read table reader macros. Okay, let's do this again. Good. And let's go to this, which is defined. Now we're going to define Cortec, and if we go and look into what we were doing before with Pandoric macros, we can actually go in and see the thread, which is the code block. Now we're not going to see every major line of code that this particular code block represents because it's a closure, but we can get pretty far into actually looking at what it represents. So if we do fourth word thread on fourth lookup of the word Cortec in our dictionary, you will see that this represents essentially a series of closures, each representing a lambda function that has a structure or set of codes that we've seen before. Those are the codes of defining a square of a square. And what's interesting about this is you can actually deal with we can actually use this to actually see whether or not something is particularly self-referential. That means it's referencing itself by essentially leveraging a feature in our Lisp REPL called print circle. So if you wanted to say do let star print circle true. Oops, sorry, I keep forgetting that I don't have that set up correctly. We can actually go ahead and print. Let's actually do this instead. Let me do this. EQ. That's fine. Let star print circle true, and then let's print star. Cut through this one. Circle. Sorry, I misspelled circle. Let me do this again. There we go. So it doesn't look like this is. Oh, right, because of the fact that I'm not actually doing self-referential anything right now. It's the way the current structure is that we don't have the kind of self-referentiality that is defined by Hoyt's book, because in our implementation we're not leveraging a couple of things that would allow us allow the inner interpreter to be able to reference itself. Because right now, if you look at these pieces of code, they are not exactly. Actually, they are exactly identical. If you look at this, they're pointing to the same things here. So there should be a way to actually go and reference this. This is odd, but I will not dwell too much on it. Let me do this. Let me try one more thing and see if this works, and if not, we'll just move on. Let's do this. SP. Does not. Here. EQ car. Let me just make sure that these are the same. They should be the same. Since they are the same, it should have been able to actually go and reference that, but for some reason my REPL is not doing what it needed to do. The point I wanted to kind of illustrate here, although for some reason I can't seem to get this working the way it should be, is that at least in fourth, this is how you would implement a lot of different this referencing itself, this ability to actually point to itself anywhere in threaded code. It allows fourth to maintain an amazing advantage in terms of keeping its code extremely concise and tight in terms of memory usage and size, memory footprint in terms of code block being in memory. And what's nice about this is that a lot of existing programming systems that that are implemented in Forth leverage this to implement a lot of code concisely, from anything from basic driver code all the way up to application code. One of the nice things about this is that the book goes on to talk about some limitations in our current Cortec implementation and our other stuff in terms of that prevents us to actually take leverage of the self-referentiality of the code. But one thing I want to point out is what this threaded code gives us is even a way of extracting only those code blocks that we need in execution, and then keeping them track of the fourth image. In Lisp, this notion of being able to take extraneous blocks out from other from the actual executable code is called tree shaking. It actually goes through the tree and shakes off parts of the tree and prunes it, essentially, to keep unused blocks from actually being part of the overall image size when you compile your Lisp applications. In Forth, this technique is extremely effective, but in Lisp, and I don't necessarily agree with this, but then again, I haven't actually found a particular use case to actually go and illustrate a counterpoint to this, but the author mentions that in Lisp, tree shaking itself may not be very effective. It may not grab everything I think part of that is related to how the Lisp library and other dependencies are structured, but that's just speculation. I can't really tell you whether or not that's true or not. If we think about this generally speaking, at some level, a lot of languages that hide stuff from the program, it is sometimes necessary to refer to have code that is able to refer to itself. Recursive functions, for example, is one reason why you have a language that has this ability to refer to itself, so that you can actually make a recursive call and execute the same code. If statements is another example that behind the scenes you are labeling something, and it will branch off to a particular location, but you could certainly refer to itself if necessary. You could do a go-to behind the scenes in Common Lisp, at least. Although I wouldn't say that that's good practice. There are certain situations where you want to use a go-to versus most situations where you'd never want to, because it makes it hard to actually inspect the control flow and the call graph and the actual ability to actually optimize your particular code block. But the technique of actually being able to refer code to refer to itself is used for recursion, looping, conditional expressions, all these kinds of things. In Forth, we want to have some way of actually being able to do this ourselves. In some cases, we may want to be able to, if we want to, for example, again, Forth, you could think of it like as a lower level assembly building up to higher level application APIs. We want to be able to branch off at a certain level to particular pieces of code that are labeled accordingly, and then branch from there. Right now, the way we've currently defined this inside of our Forth interpreter, it doesn't actually necessarily give us this ability, but the next function that we're going to be defining right now, it will enable us, or become an enabler for us to actually go through and actually add these kinds of branching examples. So let's go ahead and add that. This is, let me just go to top level. Execute. This one is going to be a top level, a new naked primitive. This is different from our defined Forth primitives. Up until now, we were using defined Forth primitives, if you recall. Let's do this here, def Forth naked prim. We were using this defined Forth primitive to actually go and set our Forth primitive accordingly, and then have it go and touch the program counter directly and set the program counter to this thread. So when we encounter it, we could just simply do a fun call, set the program counter or our Forth abstract machine, and then be able to execute that particular code block. We don't necessarily want to set the program counter in some of our naked primitives cases, unless the naked primitive itself sets the program counter. So you get more control over the Forth abstract machine by using naked primitives. But think of the difference between a naked primitive and a normal Forth primitive in the sense that a naked primitive is kind of like an assembly call that you're extending. So you're extending at the assembly level. And a Forth primitive is you're extending at the execution level of some potential block of assembly. So the first one that we're going to be defining is something called branch if. Give me just 1 second. Okay, so what does branch if do? Branch if basically does nothing more than allow us to control what the program counter is actually set, depending upon what's available at the top of the stack. So you can have, you can consider two particular branches of this guy to being two different code blocks. So let's try this. So we're going to first implement branch if by doing fourth naked primitive branch if, again nil, and this is used mainly for our primitive forms. And since naked prim also deals with other bits and pieces of code that nil is necessary. We're going to go ahead and set our program counter to being the following code. If the top of the stack is not nil, essentially, we'll go ahead and grab the decatur of the list. So it's going to be the next element in the program counter, and that's kind of the code block that we're going to be executing. Otherwise, we're going to be actually grabbing the rest of the list and having that execute. So it's either the current operation that's available at the top of the code block, otherwise it's the rest of the code block. Looks simple enough in terms of what it's trying to do, but let's see what it does in practice. Let's go ahead and set up our fourth environment. And what we're going to do is specifically, we're going to create a fourth environment that takes advantage of this primitive, and we're going to define two new words. One is our standard double function, which we defined last week, and then the other one is if then double. So let's go ahead and define that at the bottom here. And let me go ahead, do this, and it would go fourth setf, and you can totally write code like this because setf actually returns the value of the symbol of what's being set up, unless you're doing multiple of setfs in the generalized expander. New fourth interpreter, and what we'll do is we're going to define two new functions. One is our double function, and recall, folks who just joined in wondering this notation again, I defer you to our last episode where we covered this, but this is essentially allowing us to define a particular function out of compilation mode. Then what we'll do is we're going to define a function called branch if that uses branch if, either double or not doubling. We'll just go ahead and print that guy, and that's going to do either we're going to go ahead and double it, otherwise we're just going to go ahead and print not doubling. And this is just going to be if then double, and we're going to name it that way accordingly. Let's go ahead and define that. Alright, so now that we have this, what are we going to, and we can do a quick lookup here to see if fourth lookup if then double is available in our new fourth. You'll see that it is. Ooh, sorry, my mistake. I forgot to actually grab the dictionary. we use Pandoric macros. Oops, with Pandoric. Dict on the fourth. We can just go ahead and look up fourth, look up if, then double into our dictionary. And you'll see that it's there. And this is a code that actually grabs all the previous words, if you recall, and it'll just double check what's available there. All right. How are we going to use this? Double is just basically, I mean, it's pretty obvious what that function does. It takes an argument, just doubles it. But if then double requires essentially two parameters. One is the top element is then consumed and checked, and the second from the top element is only doubled if the top element was not null. So recall falsity in Common Lisp is essentially nil. You can or f is just hash false and stuff like that. All go and go down to nil. So we check to see if it's nil, and if it is non-nil, it will be doubled. Otherwise, what would happen is we would grab the code not doubling print. Remember, that's going to be converted into a code block, a fourth thread word, and then it will essentially execute that code. So notice one thing about this particular piece of code. I'm going to go ahead and give you an example, and then we're going to just discuss it a little bit. We can use this guy. I'm going to go ahead and actually dump it here. Use this guy to do essentially fourth. It will nil. We're going to check if then double. Remember, we don't need to actually in our go forth. Words are no longer need to be quotable. Nil does need to be quotable because nil is not a word in our dictionary. And when we do this, you will see that it's going to print it, not doubling, and then return the actual value of what is currently on the stack. The reason is we ate the top of the stack, so we ate nil. We checked to see if it's not nil. Obviously, that's not nil. And then we went ahead and then printed out 4 because we didn't actually go and double it. If you actually pay attention to how branch if is defined, branch if is actually taking as its next argument is a pointer to another code block, right? The control, when you're actually executing this one at a time, will go to this code block without pushing an additional resume, because remember, what does branch if do? Branch if actually is controlling what the program counter is actually being assigned to, and based on that, it will control this. So we're not adding anything to the return stack at all. We're basically just doing it like a jump. All right. In Lisp, this is equivalent to a tail call. It will actually go ahead and do the same exact thing. It will call this function without actually incurring a stack overhead, just by pushing some value into the stack to maintain what the return value is going to be. Since we passed nil into it, no doubling is actually going to happen. We're going to print a value, and then we're going to just go ahead and return whatever is available on the stack. Let's try, if we switch this guy true, let's see what happens here. This is a non-nil value, so this is automatically going to go into our doubling. This here, when we compile it, you could see is going to go ahead and return. Oops, what the heck is that? Let's go ahead and do this. And unknown value. This guy, I thought I deleted. I must have undone that and didn't realize it. Okay. And let's go ahead and do this very quickly. Alright, so you can see here that if it's a non-nil value, like before, it will we'll go ahead and dump out the doubling of the actual return thing. The main thing to be aware of what this is not so much the execution of branch if with the if then double code. The example that this is illustrating is the use of the branch instruction to extend the fourth vocabulary to encourage something that will allow us to manipulate the program counter directly, which is a pretty interesting design point that sometimes you may want to be doing it at that level. So you as the designer now have the control of deciding whether or not you want to add a particular piece to an abstract machine or not, which again I found particularly interesting when I saw this, but I would love to hear folks' responses on that. How cool that is. Let's add a couple of additional things. There's an easier way to actually go and execute and exit from a given code block or a word. And that's the fourth word, exit. One of the things of fourth, one of the interesting things about fourth is that every word that you have defined can decide whether or not it itself is a tail call, right? And again, what does that mean? Tail calls usually mean is are we incurring a stack overhead to make a recursive call or not? Okay, and that usually means are we dealing with the program counter in our abstract machine or not? The ones that we're going to be adding here, the exit call does not even deal with the abstract, the overhead of actually putting something onto the stack. In fact, we're going to be using an existing set of operations that before we defined, and I didn't define the details as to what it was doing, but now we can go through. Let me just first give you a quick review of this. One of it is related to manipulating the return stack itself. So let's go back to that. This guy. Okay. So recall that we have these two functions, the two fourth primitives in our dictionary, called that are dealing with the return stack directly. One is pushing something onto the return stack from the parameter stack, and the other one is popping something off and then returning from it. An exit call, if you think about it, is doing nothing more than moving whatever's on the return stack to the parameter stack, and then whatever is available at the top of it, we can just drop it, because that's a piece of code that we don't want to actually run anymore. We're exiting, essentially. Okay. Let me just make sure that I got this right. Right. So what this does is it will, when it gets invoked, it will deal with return stack only, and whatever in this particular code block that we're trying to execute, it'll push over and then drop the rest of the stuff out. and then we'll never actually execute a piece of code. So let's first go ahead and define this guy using our fourth standard library add function. This guy is just going to basically be simply two operations. First, we move stuff off the return stack to the parameter stack. We then drop it because we're no longer actually using it, and then we're going to go ahead and define this as a name. Right? How is this going to be used in practice? Let's go in and, let's run our standard new fourth here, and let's go ahead and define the following function. We're going to write a test case here. It has a code block. All right. We're going to go ahead and print hello. Okay. Or I'm going to go and use something a little bit more meaningful than what the book is. Start of exiting. So let's go ahead and say we're exiting this function. Okay. We're going to print out exiting. Then what we'll do is we will go ahead and exit. And the code here, and I'm going to use a simple thing here. Exited. And we're going to print this, but if folks are watching, you will know that this will never get executed. So you can think of the exit function kind of like a return, right? Let's call this exit test. And now we're going to just go ahead and exit this guy. And we're going to run it. All right. So what are we expecting? We're expecting exiting to be running. We'll exit, but this exited print will never happen, right? So let's run this and see what happens. Oops. Exit word is not found. Did I not? Hold on. Did I not define that? Oh, I may not. I may be using an existing thing that didn't add it. Let's go ahead and do this. Oops. Okay. See if this is added. We do this. Go to dictionary lookup. Exit. Yeah, it's there. All right. And as we expected, when we're defining this, the return statement executed. We popped out of the function. The rest of the code in that code block no longer becomes valid, and now we're in, essentially you could think of this at the top of the level of the fourth REPL. I'm going to take a moment here and see if there are questions before I continue. All right. So, since branch if implements, kind of a jump instruction, it's actually a conditional jump. Recall in a lot of assembly languages there are branches as well as straight up jump. Okay, I wouldn't necessarily call this a go-to. A jump is actually kind of a go-to instruction, but and branch if, I guess, could be executed as a series of go-to instructions too as well. There are other things that we may want to deal with when we're What branch if does is specifically is it actually jumps to some sort of value store in some sort of subsequent cell of the thread that we're currently executing. If we end in leverage this kind of this pattern in defining our stuff in forth, we can define other naked primitives as well that we could leverage to deal with compilation, deal with things related to actually executing and compiling our forth code that are independent of the actual execution at runtime. One of them is, say, the naked primitive compile, which will basically take whatever code is in some sort of thread block and it will compile it into a word that will be used for later execution. There are other words too as well that we're going to be defining. We could briefly define here. One is the actual fourth word here, which is a simple primitive that, according to the book, takes the last console of the code block or thread and then pushes that into the parameter stack. The version of here that's it versus what's in normal forth is slightly different. One is that, and I'm just going to quote the book here. Here in forth normally pushes the next location that will be compiled instead of the last location compiled. And this is because in traditional forth, the memory location to be compiled next is known at this time, which is normally the adjacent memory cell. But with common Lisp, and particularly what we're calling cons-threaded code, that's what we've been using up until now. There's no way of knowing this because we have not yet consed and constructed that memory. So essentially, since we haven't malloced it using C-speak, and we've not allocated that particular cons cell, we don't know what its location is ahead of time. So this is the difference of running forth in a Lisp and implementing a forth in a Lisp than implementing traditional forths using bootstrapping techniques inside of a embedded system, which is what typically forth is kind of most accustomed to. In that situation, in that scenario, you're dealing with compile time sort of considerations. What do you know at compile time when you're actually executing this code? And usually, since those are pretty fixed locations, you're not changing them at compile time, you're able to use that information to actually, in the case of here, be able to point to a direct memory location and grab that information. So let's go ahead and implement these two functions. Let's add. And again, we're not using define forth primitive. We're using def forth naked primitive. In fact, I'm going to go ahead and implement this with the rest of the stuff that I was dealing with. Give me a second here. And what the heck? Sorry, for some reason, do Emacs is just cleared itself up out of nowhere. There, right here. Okay. We're going to go ahead and define forth naked primitive. I'm going to call it compile. And this guy basically is doing nothing more than taking whatever is in the dictionary, and we are doing a destructive concatenation of whatever the current code is related to that particular top of the stack. The word, whatever word is currently on the top of the stack, and we are concatenating it with the catter of the program counter. Oops. Go. And we're also going to be setting the program counter to being the cutter. Not the cutter, the CDDR, the cutter of the cutter of the program counter. So here if you're noticing this is kind of a common theme when you're dealing with essentially trees of data, and you're in visiting that particular node inside Common Lisp, you're almost always either touching the car, the first value, the cutter, the rest, the cater, which is the first of the rest. Okay, so so if you're thinking about think about it like the second, all right, or the rest of the rest, which is kind of like the third value. So you're doing a look ahead of two symbols at every value that you're building up in your tree for our fourth interpreter. And you usually also do something similar when you're doing lexical analysis as well. So that's compile. What does here do? Here is a very simpler It's a much simpler implementation in the case of Common Lisp, our Common Lisp implementation of fourth, and that is all it does is it grabs whatever the last value is in the code block that's represented by whatever is in the dictionary currently, and it pushes this sucker onto the parameter stack. That's it. So let's compile these guys. So these are now as a part of our fourth dictionary. Now, compile and here are the final two pieces of stuff that we need to actually do fourth metaprogramming. And really, what I mean by that is writing compile time macros. Recall that fourth words, when they are immediate, they will be executed instead of being compiled into the code block of the last word defined. Okay, I'm using code block and thread interchangeably, so folks who are if you're watching, they're essentially the same thing in terms of fourth code. And in just like we can actually go and extend Lisp, we can use these kinds of immediate words in fourth to extend fourth. In fourth, though, there's a bit of a difference between what we're going to be using as our basic data structures for compilation and compile time macros, and we've already kind of brought this up multiple times, but I'm going to reiterate here. In Lisp, the basic data structures for metaprogramming macros and the basics of everything is a list, right? That's what a cell is, okay? Okay, you use cells to construct lists. Okay, so the basic of a lot of metaprogramming, where the car of the cell is an operation, the cutter is the rest of whatever you want to build, could be another S expression with more operations and so forth, or it could be a value. That structure is the basic way of actually constructing compile time based constructs in Common Lisp, or in any Lisp for that matter. In fourth, though, the data structure that we're going to be dealing with is the stack. So again, when you hear stack, the operations push, pop, top should be in your head when you're dealing with this, because that's essentially how you're going to be. And remember that it's last in, first out. So the ordering does have some sort of implication on the execution order. Let's take a simple example. Right now, our fourth environment does not have a formal conditional if. All right, and that's an if statement that checks to see if some condition is true, and if that is true, we could execute something. Otherwise, we won't. Now, we've kind of built in some sort of branching primitive through branchif to give us some ability to maybe build this out. But the way this is currently implemented is that it's very useful for scheduling tail calls to other fourth words without incurring a stack overhead. Now that we have this branch primitive, there is we can actually add some fourth code using this primitive in our standard library that will allow us to actually go in and deal with implementing this. So at this point, I'm just going to mention this is all going to be pure fourth code. We can actually use whatever we currently defined already in our core, I would guess you'd say core fourth dictionary, okay, to extend it to include some of these more convenient constructs. So how would we do this in terms of if? Well, one way of doing this is using standard library add and use the following operations. We could first say compile not, then compile branch if, then compile the no op, and return whatever the last version of it here is. And this is essentially an if construct, okay? And if you recall, we're going to use immediate mode here, which means that this code is not going to be executed, it's going to be compiled into if. All right, let's go ahead and do that. So now this is all loaded. All right. Remember what the importance of what immediate words mean. This means that if when we are in compile mode, it will be executed, and it will use these other primitives that we added, which are the no op, branch if, and not, to check to see if the condition is true to move to a different location at compile time. And that's again, I'm separating compile time from execution time, so that if you're reviewing this, you'll see that at least in our fourth interpreter that we built up until now, that one will has a distinction between what would be considered metaprogramming mode and non-metaprogramming mode. When immediate words are encountered, right, that code block is automatically compiled into whatever your target is. And in this case, the target thread compiles in 3 words, which is our not, branch if, and no op. At this point, I'm going to introduce one more piece of thing that Fort does and kind of blurs from traditional architectures. When you switch from immediate mode to execution mode to compilation mode using the immediate flag, your stack means something different. Your stack is now essentially a piece of the set of code instructions that you're trying to navigate through. So it's dealing with flow control. So in this case, it is now a control stack, not just a parameter stack. Okay. Now, while it is the same stack, regardless if you're in compilation mode or in execution mode in general, knowing that there's a semantic difference depending upon this flag, it will help you understand as you debug your Fort code as to which mode you are actually in. Let's add 2 more particular things here. Oh, so there is one more thing that I want to mention about this if statement that I didn't that I forgot to mention here in some of my notes here, and that is in a traditional fourth, if you're building if, you don't necessarily need the no op. All right, your but here we do need it because we've not yet consed, and because we have not yet consed, we don't know the memory addresses. This is what we were talking about, the differences between here and in traditional forts versus here in our current forts dictionary. So because we don't need that, we need to wait until the fourth programmer executes another word like then to consume whatever is on the left-hand side of the control stack defined by the if. So we need to define one more word here in our standard library called then. And for folks who are like, well, this doesn't look like a lot of ifs that I've seen before, then is actually commonly used in a lot of other languages. It was traditionally in a lot of programming languages to define a true block, but a lot of folks reduced the number of keywords in their languages and got rid of it and added a shorthand notation to know the differences between if you're in a true block or another block. Now, in Common Lisp, we don't necessarily need it because of the fact that we're dealing with the abstract syntax tree directly through the S expression. But and a good example of a language that has the then keyword, if you think about it, is Pascal-like languages like Pascal or Modula or even Oberon. So let's go ahead and define then. Then basically is another no-op, just constructing a const cell so that we can actually execute the true block or the false block inside of our if. And again, we're going to see other stuff that has this, but it's not in most modern languages right now, like as far as I know, with maybe Haskell. I don't know if Haskell has it or not. I gotta go and think about that. Let's go ahead and add a couple of other things. We're going to also add a way of doing negation. Okay, we're going to go ahead and there are some examples that we'll get to later on that uses some of these all together, but we're going to kind of wait before until we define all these precursor words before we get there. We're going to use negation here. And negation is nothing more than we do a swap and a subtraction, if you think about how negation actually works in the normal code. Additionally, using this negation, we can actually define an absolute value function by just duplicating, checking to see if it's less than 0. And the reason why we're duplicating the value on the stack is we're going to be popping it off when we're doing less than the conditional. So this is kind of standard stuff that you're going to be seeing in fourth code. Sometimes if you're doing a conditional, it is necessary for you to actually duplicate whatever is currently on the parameter stack so you don't actually lose that value if you need to go and return it later on. So if you're not doing any additional transformations, that actually is necessary in order for you to actually do the conditional logic. So we're checking to see if this value is less than 0. If it is, we're going to go ahead and negate it. Otherwise, we're just going to go in and return it. All right? And we'll define this guy as APS. Let's see if this kind of works. Let's do this. Define this one more time. This is now taking a little bit for some reason. My apologies. Let's make sure I'm not using anything crazy here. Memory. How much memory am I using? Let's see. I think there's a problem with my current Lisp. Let me go ahead and kill it. Okay, let me do this again. Oh, right. I better do this first. It's going to start complaining about all our predefined words here. We're using dupe and all that stuff because our defined stuff has not been set up yet. Okay. Load is the fourth demo. Please do not complain. And it's complaining about some of my examples that are defined later on. This should be fine. It's this stuff here. I don't know why this is. What? Let me do this again. There we go. Set package. The fourth demo. Oh, I named retables in. Okay. And labels are defined. Let me just check this one. Second here, because I define, I've got to. Using don't think it's liking some definition I've added. Okay. Let me do this one more time. Okay. Start. Kills itself. And it's not going to like some of this definitions here. So keep that there. Package if before it's demo. Let's go and look at this. And do a simple example. Okay. Oh, right. Because we defined it earlier. You shouldn't have to do that then again. Let's do this. Let's see, if then double exists. If then double. Dang it. This is really, really hard. Let's see here. Something is going on with my Lisp. There's something that's in the lookup that's causing this to go into kind of an infinite loop. Let's see here. I will do that. It's going to complain at some point. Word create does not exist. Okay. Here, word create does not exist. Okay. And I'll go ahead and fix this. This is there's an issue with this go forth macro not finding stuff that's already been predefined, which is odd still, but I'm not entirely sure where it's causing. Do this one more time, and then we'll just move forward and see if this because we've already defined what we wanted to define already, so it's not necessarily needed. I was hoping that all that code will get loaded in correctly. Okay, so let's set up a new interpreter. My guess is it's related to the compilation. I should have done this. Dang it. I did the wrong thing. My apologies. That's not what I wanted to do. Again, let me do this. Let's do a fourth lookup. It's not in there, but let's do a gate. See if that's there. The gate's not there. What about the plus? What is in our dictionary? There's nothing in our dictionary. Okay. That's odd. Because I see it here, but it doesn't say count 0. His problem is related to the compile word. So I have to go and look into what compile's doing. Okay. Time to try to debug compile. Let's see what happens here. Create that. Create that. Let's ignore these guys for the time being. Sorry. Okay. Set package. Okay. Now let's do this. Let's see if I can go back to what we had before. All right. Now we can get somewhere. Let's see what. Boom. Good. So far. Nothing's defined there. But let's go here. Try compile. compile should be there. Yes, compile is there. Now, let's go and slowly add stuff here. It very well could be that I could get these associated with this by doing sp slurp. That's in there. Let's see if in our dictionary. Nope, it's not. So let's go ahead and define it. And this is where we're going to have some trouble. Okay, why is it causing trouble? Do I need if? Yeah, I do need if for absolute value. No, why have I not defined already? It's probably something that I haven't even thought about. It is causing an issue. Word is not found. From which call? No word. Oh, wait. No. I think I know what the issue is, but let's see. In our definition of words, okay, so I'm going to first do this. Let's see here. I thought that this was the issue. This is not the issue. This. Oh, right. Sorry. dang it, I did it again. So I quit Lisp. That server-side close happens when I use the wrong thing in the debugger. Okay, that's fine. So now let's go and double check something here, which is our definition of this. Okay, let's do this. Move this guy over to here. Okay, now let's do a fourth load. Creates not found. So if I just simply move this guy here, it doesn't actually load. If I do this, let's do this. Let's add this here. I'm moving stuff around just to keep keep it easier to debug some of this stuff, but also there's this weirdness on defining the primitive and then using it in the standard library that just kind of looks weird. Recreate in which that's causing that. Got it. Before it's even. Okay. It's not liking the fact that unless I define it once. Got it. Making a garbage instance of. Let me do this. have this strange feeling that the reasons why is that it's not getting defined until we add it into the standard library, and because it doesn't exist, it's when this gets called, it is causing some weirdness. Create is still not found. Dang it. Let's not waste time here. Let me restart it first, because my Lisp image is all messed up. So now I'm kind of curious. We'll do this. Oops. Sorry. Okay. So where are you? Look up create. Create exists now. So compile should exist too as well. All right. Think about this. Compile actually exists in common Lisp. Yeah, that's probably one of the things that's happening. Probably. Let me do this. Let me define this guy instead of force compile instead. I bet you what's happening is there's that conflict resolution with Lisp. There's a name conflict. Just causing all sorts of grief. Okay, set package. And let's do this. Set. Do a quick lookup here. Create pairs. Let's do. Compile should be new, but force compile should be there. Okay, let's try this. Here. Do. Done. Okay, so now let's do this. Oops. And that. Compile not found. Is the compile happening here? right here. Got it. Right here. Fourth. There we go. Do that. Oh. Dang it. Go here to fourth interpreter value. Let's go compile that. Still not recognizing this yet. My apologies, I made a mistake here. Okay. This one more time. It is having trouble with I don't know. So it has no problem with if. Let's do this. And we could actually take a look into that by doing this. And there's our if statement. Let's do this one. Has no problem with then. There's done. Let's do, so it has to be a problem here. So comment this guy out and this here separately. And do a fourth standard. Add. Go. I'm separating the negation definition from the absolute value definition. The book defines them both at the same time, but I think there's an issue there. It's causing some strangeness. So now negate is part of our dictionary. See, but here. Okay. So the one thing that I could think of if it will negate, otherwise it's going to do den, which is a no-op. Let me try something. Let's do a dupe here instead. See if that causes trouble. Okay, the problem is with the absolute value definition, when it gets expanded. Alright, doesn't matter what's in that then. Okay, at least we figured that out. But now it is. Okay. How cool are you guys in us finishing this off? You guys are, just want to make sure that I'm not going over for folks. Are there questions? Do we all understand what I am debugging right now? Okay, I'm just going to assume if there aren't any questions that I'm going to continue going on this way. Just ping me on YouTube if you guys have particular questions. Folks on the Hangout, I appreciate you guys staying over. Just let me know if there's anything in particular that you want me to cover. Oh, question. At which point do you change read table? Good question. Question was related to the read table loading. I am changing the read table, I think later at the top of the function right here, line 9. Is that wrong? Or otherwise, the read table has to be changed, right? Otherwise, we had that issue in the past with the sharp backquote reader macro not being found at all because it doesn't look up there's no lookup entry in the read table. So I do change it. It's just I think later on when we're trying to compile some of the words, there is some weirdness as to it being changed. I may have changed it back to the standard read table once I've done it, but I commented that out before we started our session today, so that shouldn't have been giving us any problems, but, let's see here. Where are we? Here we go. Right here. Okay, Mr. Absolute Value. What are you doing here? Let's turn that guy off. This, here, the AMP, and it should not cause any issues. Good. Fourth. Okay. Boom. Gate is there. Okay. All right. Let us macro expand Mr. Absolute Value and see what is causing it problems. Okay, it calls the create function. Okay, what I'm going to do is I'm going to bring this up piecemeal. Delete this guy, delete this guy, and I'm going to have an if condition. Let me see what happens when I define it like this. Okay, so the problem is the fourth compilation. Okay, so let's go back to the fourth compilation. Let's try something here. Go forth, do forth, 5 for less than if print and there's our problem. The conditional is not returning the way it's expected. First line. Not abort. There is a way of actually stopping interrupt. There you go. This is not actually interrupting, it is just going into an infinite loop. There is a weird issue there. Okay, I'm going to even more simpler territory. Quick Lisp. Yes, because right now it's dead. go forth, star new forth. Actually, before I do this, let me do this something here. I'm going to go ahead and find all of our standard library adds that we added all over the place and move them into a standard location. Move this out. Okay, so now go down here, do this, go forth, new forth, 5, 4, loss. Let me see what happens when I do this. Nothing. What is our P stack? P stack. No. Okay, so let's do this. Crop. Nothing in the stack now, so let's do 4, 5. If hello print. Ah, and there we go. That is the problem. There's an infinite, like, dump. Yeah, that's not right. Why is that doing that? That is weird. Let's see. Do I have to put this in? Probably just killed it. Yes, I did. I killed it. And blew up the stack. Let me slide restart inferior Lisp. And folks, I have not yet exposed this symbol, which is why I have to go and then change packages all the time. If you guys are just tuning in. Ooh. Okay, if I have gforth installed, see how it ends conditionals. Ooh, good choice, good suggestion. I did not think about that. Do I have gforth installed? I don't know if I do. Otherwise, I'm going to do a boot install of it. But I think I pinpointed it. It's in the if statement, in the code of the if statement, that we need to go and double check. because it looks like it's creating like this massive stack that just gets blown up out of proportion. Like multiple code blocks need to be executed. Oops. Nothing in there. All right. Let's do this. Make sure that this is all good. Sweet. Okay. If hello print. Okay. What is then supposed to do? Then is defined as, if we remember, is a no op. And then it takes to here, swap it, and then store it in a location. Oh. Since we don't have any consoles already defined, I don't think that's going to work. Here it doesn't define the cons, right? Here does not define a console. That's right. Just pushing that off the stack. Swap. The swap do again. Swap basically just rotates the car encoder, right? That's what it's supposed to be doing. But the memory location doesn't exist anymore. So storing just won't work, I don't think. Yeah, the store will not work. Shoot. This is probably what's causing the issue here. There's some weirdness in the way we are defining our const threading, and the memory storage. Oh, sorry, I went to the wrong sectional code. This guy, right here. Okay, so how will we fix this? How did I fix it before? There is does 2 less than 3 print work correctly? Sure, we could try that. Give me a second here. I'm gonna have to go and restart. Sorry, because I messed up. Okay. Let's try this one more time. Kill this. Oops. Kill that, because that is not needed. Set package. Forth. Create a new forth interpreter. Now you said go forth, new forth, 2, 3, less than print. That looks working. 4, 5, less than print. Got that working. If hello print. See, this is where it's going to cause some trouble. which is if we run this, then is kind of expecting that there should be a storage location. But instead, the then should not be looking for a storage location necessarily. Let me go and look at, maybe I messed up how I implemented this code. I was porting it over from what was available in the book, but maybe the book is incorrect on this. Then name immediate. Okay. If is if immediate to if is immediate. Okay. If is immediate, compile no op. Got it. So the location of the code is going to be the location of the no op. Right. Okay, I see where it's doing. The no op there is sole purposes is to cons a location for us to store something. Most first sometimes position but here right. So what this code is supposed to do is so I'm going to try and explain this here as to why some of the issues might be arising. The if code has this no op on line 321. Okay, the no op's purpose is to kind of maintain the location that we need to execute if turns out to be null, like the condition turns out to be null. But since we don't know where the else condition is going to be jumped to, we need to, or even the true condition needs to be jumped to, we need to keep this location available so that when we run like a den, the den keyword, which itself is a location, that we're able to then swap the two and store whatever the current location is, which is the location of the den, and replace it with whatever the location is of the no op is on line 321 when it's compiled. So that way, when the execution happens and the condition turns out to be true, we just need to skip all these instructions and go directly into the else clause. If it turns out to be false, sorry. What's looks like is happening here is that it's having trouble actually storing the location of the no-op over to the it's overriding the location of the first no-op with the location of the second no-op. I know it just sounds kind of weird when you hear it that way, but that's what I think is the problem. Let's see here. Okay. So now, let's see here. Let me run this code, which is running. I run this. It just blew away my there it is. I was wondering where all that is. This is just an endless amount of stuff being pushed onto the stack. So, why is it just being pushed that way onto the stack? That's the question. That's telling me that there's an issue with the... Actually, I think that is doing the correct thing. It's just that we're not retrieving what's available from that closure. Okay. This is odd. But I actually think that this is actually working the way it was supposed to. It's just what we're expecting is that it would return some sort of closure in there, but instead it's actually not returning the closure directly. Instead, it's returning the storage location that's holding the closure, which I think is wrong. Let me see what I can do here. First, let's go up here. We store it. And we grab the car of it. And that way we replace what's actually in that memory location. So we're not reading in the memory location, we're actually just grabbing what's in that const location. I think that's all we need to do. Let me see. I may have to boot restart my Lisp because it's currently in an infinite loop, and we'll see if this works. Oh, right. My apologies, I forgot to. Let's do this again. this? It's gonna still be an infinite. Yeah. Dang it. See this? This is what's causing the problem. Okay. Let's do this now. Oh shoot, I did not realize it was 5 o'clock already. Okay. I can't let's see. This is not gonna work. Slide restart inferior Lisp. Sorry, folks. I just am constantly butchering the steps that I have to do this here. Sorry about that. Set package, not set directory fourth. And if print. Okay, I'll try that. Do that. Go forth. Four, five, let's print just to make sure. Oops, one. A mistake, I forgot to pass it for my fourth instance. Set F, fourth. There we go. Done. Done. Make sure my stack is nil. Good. I don't think that's going to work because it's going to go into that infinite loop. This is what I was kind of expecting. And the reason is this is happening is related to that store operation. Not in the store operation, in the branch if. It has to be related to the branch if. What is the branch if doing? Here we go. We pop it off and we grab the cutter. And more importantly, it's a combination of this last word, this here, that's in the if statement. Basically, the core of this issue is that the stack is blowing up because it keeps on pushing using that here instruction, the last word of the dictionary. It's the same last word here. If you look at it, it's the same exact memory location. So there's some weirdness going on there that I have to go and debug. Since it's heading on 5 p.m. here, let us continue looking into this next week because I don't want to take too much of you guys' time. And we'll get started because this is really the last piece before we start implementing Lisp in Forth. So once we get this if statement and branching logic in and corrected, next week we're basically implementing a basic Lisp using Flubify and the Flubify macros that are defined in the book to finish off our excursion. Might be worthwhile tracing here. Okay. So we have a good suggestion by Richie Primus about tracing. I don't know if that would. I will try this one thing here, and if this doesn't necessarily work, I will try and debug this and get it corrected, because there isn't anything code-wise that doesn't match already what's available. So we may need to correct something in our implementation to get it all working. But let me try that. Yeah, you're right. We should trace if. That's correct. I have to go in. Can I just do tracing on a single? No, there is. How did I turn on tracing of the execution code? It's a profile. Yeah, I could put a break in there. That's a good idea. Actually, we can't do that, can we? Because we're in our fourth interpreter. We need to do it in the inner interpreter, not in the actual code. Let's see here. I may have to do this. Restart. Just because of the fact that that's still consuming memory. I need to. Once it gets into that weird state, I have to go and corrupted my Lisp image. I have to go and blow away my Lisp image and start from scratch. There we go. Set package. Go forth. Yes, and I will go ahead and push in the latest code so that folks, you guys can experiment with this as well. Let me in fact, do that right now in the time remaining, just so that we have that local projects, CFD, fourth download. Okay. Updates. Alright, the code has been pushed for folks who want to go and get the latest code. Um, it's available on the Atlanta Functional Programming GitHub repository. In our remaining time, let me just see if we can quickly get our structure going here for the if statement debugging. Otherwise, I will set this up, and then next week we'll go over it as part of our initial code review before we move forward with new material. So the way we would have to do this is since if is being interpreted as a func call, we need to go into the inner interpreter function, which we defined way above here. And we need to essentially handle the cases where we are pushing in stuff and see what's going on. One thing to note, we need to also update the print functionality for the definition of the naked primitives, because the fact that branch if and not necessarily, because not's a Lisp function that we've defined using unary word definer, but certainly here we need to are all manipulating the program counter directly. They are not actually adding anything onto the return stack. And that might be causing some of our fuzziness here, but I doubt it would be the case given the fact that what it's doing behind the scenes is dealing with particular code blocks and making sure the program counter is pointing to the right code block before it executes this. So I need to do some digging into myself as potential areas of this causing this issue based on what we've currently implemented into this. And yeah, I'm going to go ahead and table it now and wait until next week before we cover this issue and go through it in more detail. So thank you all for joining. I do appreciate folks who have been joining in the 3-hour limit here. Next week we'll finish this off and try to get the Lisp in fourth implementation going and debugging that. Are there questions? Before I let you guys go, as a reminder for folks, Atlanta Functional Programming is going virtual in terms of our talk series. We are looking for interested speakers to give talks. If you have a talk topic related to functional programming, Lisp, Common Lisp scheme, even Clojure, we are open to it. Give us a talk topic, and we will schedule you in. Please DM either me as Bugram or Dagmar on Functional Programming Slack, or those of you who are in the Atlanta area, Tech 404 as well. And I will see you guys next week.